Hi all, this is Claudio from expertfea.com recording for you the 7th webinar meant to help you improve your finite element analysis skills, especially in ANSYS Workbench. Before starting the simulation work, let me remind you of our website expertfea.com, where you can find news about our activity in FEA, lots of tutorials, already solved FEA cases, books, webinars, FEA news, partners page, and you can contact us if you are or you desire to be our customer. So, getting directly to the subject, on GrabCAD.com I discovered a nice and simple geometry that we can use for today in order to make a dynamic or kinematic analysis. So let's download this file. It's part of a camshaft assembly from the distribution of an engine. Let us download the step file. And as I always advise the FEA engineers, let's open it in the ANSYS Spaceclaim and prepare it for simulation. So, here we have the cam and the follower. There is a plunger here with the valve, a spring, and this small case through which fuel will be injected. Let's look a little inside. Yes? We need a section view. So as you see, two of the axes are highlighted. We can select both of them with Control pressed, then click the section mode button. Suddenly section is created. We can clearly see that the geometry is very nicely done, except the fact that this plunger is not properly aligned here. We will need to align it. The valve, let's say, we need to align it to this hole. And what I do not like is that the spring touches on a round surface, this face, and this, upon pressing the valve, upon pressing and compressing this spring, can impose lots of stress here on this small housing, let's say. I would like to flatten this surface of the spring. So the geometry is pretty straightforward, cleanly done. Let's ensure that we have a proper alignment here. First we can increase the radius of this hole, let's say 4 mm for clear view, and we will select the align button. This first face should be aligned to the second face, and now they are perfectly centered. Let's just for confirmation, let's select the axis. not so easy sometimes. Let's just select the faces and see what happens. Nothing. With triple click we can hide the valve, and now we can easily select the axis. Section mode again. Yes, we center. Right click, show all bodies. And now we can see that the valve, which is already also plunger, is perfectly centered here, okay? So, as I said, what I would do is I will extend a little this face. The pull button is already activated. A little means, yes, 0.3, why not? Also, here. Here it doesn't work like this. Here, this face we cannot simply extrude it or extend it because it will not be, let's say, feasible from the production point of view. Instead, we will just move this housing upwards a little with 0.3, alright? This is the small housing, it's called body here. We press the move button and we go up, yes, and just write from the keyboard 0.3. Alright, this is done. So we have interference with the spring, and this is what we wanted, yes? Let's click the combine button. We read, yes, the messages, click a target object. This is the target. The valve is the target, yes. And now it says click to select a cutter object. We need to cut it with the spring, yes? So, what we observe is that there is also another body created, an extra body, yes? We can click it and it will be removed, but it's not what we needed. We will just delete it later. We can select this body, click delete, but it's not what we wanted, okay? Instead we wanted to cut the spring, not the valve, yes? Let's repeat the command. The spring should be cut with this, with the valve, yes? Let's go to the spring and we observe this extra portion that we need to delete. Yes, now we have a very nice touching surface. Let's repeat the command. Combine, the spring is the target, it should be cut with the body. Escape. We select this extra portion, click delete, and that's all. This is what we need. Alright. Here I'm not convinced that this protrusion, boss, whatever, is circular, so I will create a hole. I selected the face and I will go to the sketch mode. I click the plane view button and let's just try and create a hole here in the middle, alright? 5mm is fine. we click the face and just push it. Alright, maybe with more force. Here is the hole. The fact that it touches here is very nice, and we agree with this. Or it will touch, because now there is a cap. Let's extend a little this chamfer, because it's not important now. Here I would like this edge to be round. You see that the default for the pull option is round. It can also be chamfer or whatever. Let's push a little. Just see. Alright, we can write 1 from the keyboard. It's done. Alright. Triple click will select the body. This is our cam. Sincerely, I do not like this protrusion. Let's perform a cut. This is what I like. Alright. So I think this is everything. I want to look a little here. Maybe extend this face a little. Just a little, until it almost touches the valve. 0.03 is perfect for our scenario. Let's hope we don't have any interference. This awesome modeling tool has the repair toolbar, in which you can access lots of healing and optimizing methods, but the prepare has the interference button, which is very useful, because it told us that we have an interference here. Alright, so let's just escape, and we will pull the face with 0.01. Yes, we go back to the prepare, interference. Yes, interference again. Alright, click, design, pull, go back 0.01. Prepare, interference. Oh my god. No errors found. Finally. Can we simplify something? Sincerely, we'll leave it like this. Why not? In our FEA, for the moment, we don't need this radius. We can just delete it. Also the inner one. Yes, in order to have a coarse mesh. Triple click, hide. Let's look if we see any radius inside. We do not see any radius, but what's with this face? The spring looks a little weird. Yes, very weird. I think there will be problems with the solving, but let's give it a try. Alright, this radius is not needed. I do not, sincerely, I do not like this boss here. I do not see its use. We will try and just extruded. Alright, pull and ta-da, out, show all, and now we have very clean geometry. Alright, show all, file, save as, yes, I will see here optimized. Close Spaceclaim and open ANSYS Workbench. What we will do is make the assembly work, and hopefully the spring will be compressed. Transient Structural. Let's put a date here, 2016, June 30, optimized. Here, F2 button, meaning rename. And we will browse for the geometry we just created, or I just created, in this case. So, once the 3D model is being loaded, we know that the parts that interest us are the spring and the rocker. So all the other parts will assign them rigid behavior. So the body will become rigid, the cam will become rigid, also the valve. Right click on contacts, rename based on definition. And here you need to click body views in order to inspect the contacts. Let's see the first contact. Is a bonded contact between the body and the spring, as seen here. It received a question mark because it needs from us to flip contact and target, to flip the sides of the contact. The sides of the contact in ANSYS are called contact, which is the source, and the target. The other contact is between the valve and the body, and is not of interest in this FEA. We will leave this contact between the spring and the valve. We'll leave it as it is. Also, this this contact between the cam and the rocker needs to be made frictionless. And of great importance here is to change the normal stiffness of the contact to 0.1. Contacts can be seen as spring elements which have their own stiffness. If we leave the software to assign whatever stiffness it wants, then a convergence will not be guaranteed. So let's do the same for the other contact. Change its type to frictionless and make its normal stiffness to 0.1. Also, a good practice is to select the bonded contacts and change their formulation to MPC, or multiple point constraint. Alright, let's make this assembly move. This means that we will apply a revolute joint here on the cam. Let's click the inner face, body and ground revolute. This cam will push the rocker, which will swing here, will pivot according to this face. So let's assign a revolute joint also here. Furthermore, we'll need this valve to translate. We can do this in two ways. Either we'll select the valve and assign a translational joint, or what we can do is make it translate according to the body. Yes, so we can change from body ground to body body, and here on the yellow row we can select this face and we have a reference. So between these two bodies we have a translational joint now. Also, let's fix this body. We'll click this face, body and ground fixed. Alright. Right click, mesh, generate mesh. We will see that the mesh is pretty coarse. So let's change the relevance here to 35. You can change it to whatever you want later. Nothing great really happened. Maybe 50. We can see that the spring is a little finer mesh now. Also, let's make the rocker part with the finer mesh. Element size 5. Is it enough? Let's see. No. Then it's 2.5. Yes, now it looks nicer. And of great interest are the faces in contact. This face on the cam and this on the valve. Let's assign an element size of 1. And for the other faces, let's select the body, hide all other bodies, mesh control sizing, the contacting faces, we receive an element size of 0.7. Let's generate the mesh and see the modifications. We can see now that the mesh is very nice here, yes, and the elements are similar in size, let's say. Alright, let's assign the rotation. It will be in 4 steps. With Shift or Control pressed, we can select all the steps and assign the time settings. 0.1 initial time step, carry over time step on, 0.05 minimum time step, and 0.3 the maximum time step. Let's assign the load joint a joint load. We'll use some degrees. We'll begin with 45 and end with 180 degrees. We prescribed only half a circle, half a rotation, because this is the, let's say, the useful range, the useful area that will allow the rocker to be pushed. Yes, then the valve will be pushed down. So this is why only half of the circle is important now. This other half is of not big importance. So let's ask for output. For directional deformation, we will choose the valve according to y-axis. Also its directional velocity according to y-axis. Let's see what happens in the spring regarding its strain and its stress. Also, let's see what happens in the rocker body. Let's check what happens in this Revolute joint, probe joint, this one, and we will investigate the contacts, not the bonding contacts. We don't care about the status, but the pressure. This is more important. So we can assume that the pre-processing is done. We need now to solve it and see what happens. We click Solution Information, and if we are not familiarized with what the solver writes, we can go and change from solver output to force convergence. We can see that the initial time step is a little too high, so maybe a bisection will occur. Solving convergence problems is a great art and requires a lot of effort and a lot of trial and error. The general idea is to, when having convergence issues, the general idea is to ensure that the geometry is correctly made, meaning that there will be no big interference or big gaps, and also that there are no geometry errors like shell bodies or others. Also the contacts need to be investigated thoroughly. Remember, the body views this button, and we can zoom in, zoom out whenever we want. Also, we can change the mesh. Usually making it finer will help in making the solution converge. And in ANSYS settings, making the time steps smaller the time increment smaller, usually help in convergence. Also, last but not least, the discretization, the incrementation of the load can be also decreased. So let's see what the solver is doing now. Look, convergence appeared, and will return in a few seconds after the solver works more. Yes. So it seems like the FEA is converging pretty well. We're close to the end. If this view is very confusing to you, remember that you can change the display points to whatever number you want. I usually choose 35. And instead of forced convergence, you can just play with other plots. You can look also at the time increment, even though it's not very useful because they don't show the exact value. From what I know, it's 0.05, as it can be seen here. It goes from, so it's the minimum time step that we assigned here. So let's see what the results will be now. Because we apply the rotation, we will also ask for angles and other output, which can be accessed after the solving is done if we press the worksheet button shown here. So remember, for user-defined result, yes, after the FEA is done, you can press the worksheet button and access lots of new output. So the FEA was solved. Let's animate it a little. So behaves very nice. This is the total deformation plot. Let's see the valve, how much is displaced. This plot is not very revealing because it's on the x-axis and we need it at the y-axis. So right click, clear generated data, and let's choose the y-axis. Right click, evaluate all results, and now it's way better. It shows only this face because this is the face that is in contact. It's part of the contact with this rocker, let's say. It shows this face because it's part of the contact with the spring. If we choose the part to be flexible instead of rigid, then we will see the entire part colored, let's say. Nevertheless, 2.78 millimeters down. The velocity, the maximum is, so it oscillates, let's say it varies between 3.5 and 3.25 millimeters per second. So this is the strain in the spring. Which is very low. This is very good. Also very revealing is the stress in the spring. Let's check where is the maximum. Here where the first coils collide, let's say. And for the maximum value, this value, right click, retrieve this result. If we assign, let's say, if we know that the yield stress is around 250 megapascals, then we can access and view more colors close to red. Okay, not so more. Let's make 100 and see. 100 is not a realistic value because, as I told you, 250 is, let's say, the yield value for common steel. So for the rocker, this is the strain in the rocker or the follower. It behaves exactly as we expected. We look in the contacts, and here in the joint, this is the stress. Is the highest in the contact with the cam as expected. 24 megapascals is negligible or neglectable. You can see the force that it develops in this joint. If it's not very revealing to us, we can look on other result type. Constraint force looks the same. Let's look on moment, total moment. So we have a maximum 45.6 Newton millimeter moment in this joint. And last but not least, very important, the pressure in the contacts. You can see how the contact line changes, or the contact patch moves together with the contacted faces. Also here. And the values are very low, let's say. As I told you before, if we click solution and access the worksheet button, we can ask for angles. Our rotation was about z-axis. Let's choose Rz here. Angular velocity according to z-axis. Angular acceleration we have. Stress, strain, temperature, force, energy, moment. Angle, x and y give z, x and y give z, axis, displacement, and whatever. Right click what you selected with Control pressed, create user defined results, and here evaluate our results. So let's see, these are some angles as we prescribed. Yes, 180 degree is the maximum on the cam. rotational speed. The biggest is here, 1.5 radians per second, as expected. This is a angular acceleration. Not very revealing. We're looking for a moment alongside z-axis and nothing happened here. Let's delete it. We have angles. Not extraordinary. Let's change from XY to XZ and let's see what happens. Not too much. Okay, you can play yourself with other values. Y, Z. And here let's change its name to YZ. Yes, not very interesting. Here, this is what we were looking for. Let's delete this. We're looking for this. Although it's XY and it's not very interesting. Let's duplicate it and change from XY to XZ. And here from XY to YZ. Right click, evaluate our results. So feel free to explore whatever new output you can get from this software and use your imagination in order to improve the solving, the meshing, and finding new ways to simulate the real life behavior of mechanical assembly. This being said, I wish you a nice day and best of luck in your career as a finite element analyst. Bye bye.